Okay, so let me just start a little bit with this slide. So in the Food and Agriculture Organization, we strive to make the world a better place where everyone can securely access sufficient, sustainably produced and high quality food to lead healthy and active lives. So the Agro-informatics platform is one of the tools that we have developed in order to help us in that mission. So the objectives of the platform are to support decision-making, interventions, design, monitoring and evaluation. As we've heard, we're covering many different topic areas, all related to food and agriculture. So from soil, land, water, climate, fisheries, livestock, and many, many others. And it's very difficult to do anything in the space of food and agriculture without geospatial data. The characteristics of the system is that we are striving to make it trustable, multi-sectorial, interoperable, standards-based, and coming with documentation or metadata on the data. So during the last few years that we've been developing the platform, we've had these sort of mantra that have been driving us on how we should make decisions and what we should do next. Which I think are interesting, so I'll share them with you today. So the first one is that we will ensure that those that are authorized can find and consume up-to-date data conveniently. And then we will harmonize data, increasing its consistency, compatibility, comparability, and compliance. The data will be well documented, so that we know its digital rights, its provenance, and any usage qualifications. We are uniting all of the data in a catalogue to create a comprehensive, holistic view, rather than having data fragmentation. And I'll talk a little bit more about that as we proceed through the slides. So firstly, what kinds of data are we talking about? Well, we can distinguish it in three sort of broad areas. The first is the format of the data. So we're supporting tabular data, and then the more typical geographic data. So that's either raster or vector-based. So the important thing to note about tabular data is that we always have some way of knowing where on the planet Earth it is. And for those, I guess everyone in the audience is familiar, but a raster data is dividing up the planet Earth into grid cells or hexagons where we have assigned a specific value. Another way that we can distinguish the data in the platform is whether it's a flat data structure. So that could be the location of a market with some attributes about the facilities in the livestock market, or it could be a multidimensional data set. For multidimensional data sets, it means that we can look at the same unit of measure, be it precipitation or the vegetation, and we can look at it through different dimensions. So it could be the dimension of time, or the dimension of season, or species, or crop. So this is what we intend by multidimensional. The last way we distinguish data is on whether the data is federated or ingested. We strive to federate data whenever we can, and as long as the data is following standards, that becomes relatively easy. However, we are always dependent on the availability of the services that we federate from. And sometimes that also means that we're unable to do more advanced analysis that I'll talk about later in the presentation. So the alternative is that we ingest the data and then we republish it. So we republish the data following standards, and that's the other way of doing it. So the final method is whether it's static or stream data. So static data is data that's typically manual. It's a one-off piece of work, it's been published, and it's not regularly updated. Stream data or automated data is a data set that's constantly changing. So it could be a daily, hourly, monthly. So there's some kind of frequency of the data being uploaded, and you can't really have a human sitting there doing it. You have to have a data pipeline in order to support it. So the way that you access the platform is through the Data Explorer, and I'll talk a little bit about that next. So the Explorer is the primary point of access. It empowers you to explore and analyze geospatial data easily. You can access it through any standard web browser. It works on a mobile device, and no special plugins or extras are needed. It's currently available in 5 languages, and we expect to have Arabic also by the end of the year. The system comes with an online tutorial, and it's being built on an open source solution, Terrea. And this is being developed in Australia by the Data 61 group from CSIRO. So the purpose of the Explorer is to help you to search and find data, perform time series analyses, do side-by-side comparisons, visualizations, geospatial analysis, create reports and stories, and it comes with built-in support for areas of interest. So this is a typical shot of the platform. You can see here that we have what we call themes. Within a theme, we have a group, an agricultural stress index. We have an individual item, and then the item comes with a metadata description. You'll also notice in this case it's a cube. So whilst we're looking at the unit of measure stress, we can switch that between season or cropland and date. So these are 3 dimensions that apply to this data set. Built into the system, we have this concept of well-known areas. And well-known areas allow you to perform analysis or to create chloropath maps based on data sets. So examples include fish catch areas, they can be land parcels, they can also be administrative districts or hydrological basins is the one on the top right. So what that means is that if you have data in the platform and it's using a well-known area, so this is an FAO data set, and it's using M49. M49 is a well-known code for identifying countries. So that means by publishing a data that has a column M49, and it also has this other column called year, the system itself will automatically be able to firstly color a map based on the data, that it's using the M49 code, Angola 24, to work out how to color it. It also means that we can have this date time slider here. So if we click on Angola, we have what we call a feature info pop-up. This is giving us a summary of the data at that point. So we have a quick spark chart. We can also now pin this spark chart into a charting area at the bottom, and then we can choose another country. So let me take Tanzania and do a similar thing. And you'll see now that we can have a second line and a third line. So I've added Zimbabwe, Tanzania, and Angola. And this allows you to do a very quick analysis that's very easy for the data producers. They've only really had to provide the data, including a well-known area. The well-known areas, here's an example where we're using georeference survey data, and we're using administrative districts at the level 3, and they're following a well-known code, and therefore these maps can be created. You see that there are several units of measure in this case. Another way of having data within the platform is anything that includes a latitude and a longitude. So this is FAO's animal health master database called Empress-I. And here we can filter on different things like the disease diagnosis and such like. And this is the full record as it's in the database. So by doing these queries on the left-hand side, we'll see these dots appear on the screen. If I click on a dot, I'll get a summary. I can go to the detailed report, and I can also search the publications database. If I change the time over here on the bottom left, the dots will move around because now I'm interested in a different time period, so the outbreaks of this particular disease are in a different place. And I can continue to do that changing time. I can also change time by using this little play button that will just loop through the time that's available, or I can jump to somewhere along the timeline. Alternatively, I can just say, just show me all of the data that corresponds to my my query. So these are all of the outbreaks that match the query. Data in a tabular format, so also the previous one we saw, can also be shown in a table. We can use the table to filter the data that's displayed. So here I can say I'm only interested in domestic sheep over here. So now the number of dots displayed will be different. I can also download this data in a CSV or Excel format, or I can create a quick pivot table that quickly allows me to look at the data. So here I'm looking at a heat map, and you can see, for example, camels and Mauritania jump out as a high number, or Madagascar and cattle infections. So the other thing that we're supporting is spatial disaggregation through various models. So on the left-hand side, we see a subnational breakdown that's being provided into a model to provide a pixel-based or raster-based breakdown of cattle density. I've talked a little bit about cubes. This is just another graphic showing that. So we're looking at agricultural stress, comparing seasons and cropland. We can compare over space and time. So another data set that we have on the platform is, for example, so we just look at this one, what we look at, cattle density in heads per kilometer squared. And then on the right-hand side, I have human population density. And so now we can quickly compare the two. In some cases, it's important to compare these two, but we could be comparing any two variables. Now we can combine those together with the disease outbreaks. So in this case, I can see a disease that affects both humans and cattle, and I can see the occurrences and how they're being shown. We can also take one data set and do a side-by-side comparison. So here we're looking at something from the VAPOR database, another FAO data set looking at water, in particular water productivity. And one of the variables is transpiration. So I'm taking two different dates that are year apart, and we can see this side-by-side comparison. The system comes with inbuilt facilities for printing. So we have this idea of templates for printing. And you can also just share what you're looking at by creating a custom link with someone else, and they will see the same map or configuration you were looking at. We can take that a step forward by creating what we call a story. So you take screenshots of the platform, you annotate them on the particular piece of data that you're finding interesting, and you create a little story composed of these slides. And when you're finished, you can share that story with a colleague, and then they will then see the same interactive story, the same maps. They can interact with the maps directly, and you can get the points across about the data. We have included facilities to download the data. Raster data is typically in GeoTIFF format, in cloud-optimized GeoTIFF format. And you're able to use well-known areas or draw an area to crop the data and download it. So this is an example where we're cropping a bigger data set for analysis in QGIS. So the system comes with many different analysis on models. So what do? They transform raster data. So, for example, reducing it by finding minimum, maximum, median, standard deviations, or counting classifications. Or we can provide more complex raster arithmetic, looking at overlays and masking and some more custom formulas. We also provide tabular data to perform multi-criteria decision analysis. So you might be looking for a region that matches some combination of characteristics. We also have more complex analytical workflows, and these are typically either composed to smaller workflows to create deeper insights, or they're integrated with a custom model. So it could be a machine learning model, a model running on Google Earth Engine, or provided by some external partner. The internal analysis system we've developed ourselves, built based on open source products again. So it's developed in Python. It's completely cloud native, so it will scale with the number of backend computes necessary. One of the things you can do is to link analysis to well-known areas to automatically keep up to date a set of statistics. So, for example, the rainfall in a district, as each new rainfall image comes, the statistics will be automatically generated. So here we're looking at a combination of another side-by-side comparison. This time we're looking at precipitation anomalies in the past, predicted in the future, and we can see them together. And we see our first piece of analysis. So this has looked at the long-term minimum and maximums. And then, so that's going back to the whole time series. I think this might go to 1960, I don't recall. And then we can see the last 4 years, and so that you can see any sort of things that stand out. So you'll see that this blue line, 2021, was much lower rainfall than typical for June. We can do another kind of analysis is sort of class count. So in here we have an area. In this case, it was drawn, but it could have been a well-known area. And we can see the composition of the area using, in this case, a Lankover classification. We can do the same at parcel level. So we're looking at field A, field B, net primary product. And again, we can see the data in a table, download it, filter the tables. We can also connect to models that return raster imagery. So in this case, CPAL is another FAO product. Looking at forestry with some sophisticated models. You can provide the inputs to these models, and as a return, you will get a raster image that corresponds to the query or the parameters that you provided. We come with many different backgrounds. So we come with some high-resolution satellite imagery. But we also have many of these sort of standard ones like the dark background, no labels, place labels, etc., etc. The system also supports 3D. It uses a product called Cesium in order to do that. So we have two mapping components. One of them is Leaflet, which is light and fast and works on a mobile phone very well. And the other one is Cesium, which is a bit heavier, requiring a bit more bandwidth and more power on the computer. And you can see here we've taken a two-dimensional layer. So I've stayed with the Lankover classification. This is the 10-meter European Space Agency data. It's actually coming from Google Earth Engine, and it's been rendered through a standard interface. So we're taking source data from Google Earth Engine in 2D, and we're draping it over a 3D model provided by Cesium. Another kind of analysis is where you look at many different data sets. So the back-end analysis function here is looking at sheep, cattle, goats, precipitation anomaly, many different factors. And that allows us to then get this sort of this radar diagram showing the relative risks of two different areas in Kenya in this case. And we have some charting that's going with it. And in fact, this is part of a PDF report that's generated regularly. One of the things we're working towards on analysis is to provide support from open Earth observation. So this has been spearheaded by the European Space Agency, but NASA and JAXA and many others have already signed up to it. And we think this is a very powerful way of moving forward in the future to be able to connect many different back-end processing systems together in an open and standard way. So we currently don't support this. It's something that's coming soon. We'll hopefully have some of the first stuff available by the end of the year. The data catalog brings together all the available data in one place. So the idea is that you can search to find relevant data sets. You can provide a preview of that data set. You can have some quick interactions with it, but it's not like the full Data Explorer. And then you can download the data for your needs. The formats that we're using to document the data is so predominantly this ISO standard. So this is this 1911.5, which I'm sure many people have heard of, which is a standard way of documenting your data. But we're also using CCAN, which is an open source knowledge platform, which has a lighter metadata standard. And we getting very close to supporting publicly Stack, which is a de facto standard more, I think, machine-to-machine operations than anything else. But we will soon be publishing in Stack. So this is a spatial temporal asset catalog. So you'll see people like Microsoft using that, Google Earth Engine catalog. Many people are using that. So the catalog itself provides a unique identification, detailed description, version tracking, rights and provenance, and quality information, along with many other fields. I'll skip this slide in the interest of time. Here's a typical kind of metadata entry. So you'll see you've got things like the fact that -999 is a no data value. You've got who to contact. You've got the copyright, how you should cite it, data lineage. I see in the audience we have someone from eLeaf who are our partners and are producing this data set. Okay, so the other thing that you have seen, talk very briefly, we have a site, which I'll go into in a minute, and then we have these themes like crops and vegetation. And in themes, we have groups like agricultural stress, and then we have an individual data set, which is documented. So the metadata catalog sort of works this way. We have an organization, let's say it's the University of Twente. They can have several data sets. Each data set can have several resources. They might be different expressions of that piece of work. And finally, there are views or well-known ways to, by default, interact with that data center. There is a concept of a user that belongs to an organization and has certain rights. So the rights here are derived from CCAN. So you have the idea of super admin, an administrator, editor, member, and a visitor. And this allows you to only share data with some people or to allow people to edit data but not publish it. And it gives you some control. It's at the organizational level. So if you have a statistics unit that is publishing data, they can decide who can see and do what with their data. The way that you get data into the platform is firstly you need an FAO sponsor to set up the account. You upload your data or connect your data. You then provide the styling and the presentation. And then if you would like also to represent your institution by creating an organization. And then in the case that you're publishing data publicly, you will need to seek some clearance for publication from the head of profession here. Finally, as your own data owner, you have some ability to customize the themes, channels, and applications where your data can be used. So let's talk about some use cases. So these are some of the places where we're already using the platform. It's a little out of date, but it'll do for now. We have market-based transformation of agricultural systems, water stewardship, animal disease management and epidemiology, climate-smart agriculture, crop production and early warning, ecosystem restoration, soil data, land cover, crop calendars and phenology, and smallholder advisory services. So these are some of the sort of use cases that we're seeing that the platform can be applied to. So let me dig into one or two of these use cases. So this is the flagship hand-in-hand initiative from FAO, where we are connecting donors with people with needs, and we're trying to make those investment decisions data-driven. So through the platform, we're able to, first of all, do this higher level topography analysis by combining, for example, the potential economic status efficiency to generate this traffic lights on where we should invest in this particular value chain. And then a second step is undertaken where we are then looking at the situation analysis. So given that we've decided, this is building a crop storage for rice. So here we are combining many layers in a sort of a multi-criteria decision analysis to highlight some areas where we think would be the best place to build this infrastructure. So it's looking at, do they have banks or internet, or do they produce there? Is there a market there? That kind of thing. And then the next step is that then they're field validated and confirmed on the ground. This is an example where we are using the platform to be serve a specific community and a specific purpose. In this case, it's a national community in Tanzania. So they are deciding which data from the catalog to include in their portal. And they're customizing the way it starts, some of the branding, and the data sets that are visible. This is one on water accounting. So here we're pulling data from many different data sets together in one place to basically look at the supply, demand, and flow of water use. So this is a community, this is a thematic-based one, which is still global. Here's an example of one that we put together with Libya. And this is looking at water in particular at a very detailed level. So this is not only thematic, but also regional. In fact, it's only certain portions of Libya that are covered by this project. Here's one on agricultural stress index monitoring. And you can see that I can step through time. Here's one on epidemiology. So we're looking at a model running on, in this case, Google Earth Engine to predict the likelihood of mosquitoes over here. And the mosquitoes are then going to bite these cattle over here. And then we can see some analysis on trends. So it's another example of applying the platform. We're also using it for climate risk assessment and, in fact, generating reports that show that you've done due diligence on where you're going to plan an intervention before you jump in and spend the money. So yeah, we're looking at these sort of these key areas of vulnerability, exposure, risk, and adaptive capacity. And then that generates reports that can be attached to project proposals to better understand that. One on animal production and emissions. So I'm going to zoom through these before I run out of time. This is the soil portal that we have, including things like the soil organic carbon model, salinization, and many, many other different soil attributes. This is a project that's looking globally at ecosystem restoration. So this is more a monitoring and evaluation. Here we're looking at a data service coming from the platform, in this case to drive an external model. So we're looking at the crop water requirements for maize here, and we can pull some of the data from the platform, some of these climate parameters. And then based on the actual location that they chose within the Agro-informatics platform, they are then able to go through and see the water requirements in their particular area for that crop. Here's an example where it's been connected to the digital services portfolio, which is providing advisory messages to farmers. Yeah, not more to say there. So we talk about some of the data management tools. So essentially, the way that we're publishing data is tabular. The data itself is predominantly in BigQuery, which is a product from Google. And we have this table manager that is managing the update and the publishing of the data in a data warehouse, and then annotating the data so the data can also be used for machine learning purposes and other things. Then we have a vectorial workflow. Presently, this is with GeoServer, where we're looking to move that to a cloud-native format at the moment, and that's very active. And certainly by the end of 2025, we will have replaced that by cloud-native solutions that don't require a server in the middle. And then over here we have the raster management. And the rasters, again, are now already in a cloud cloud-native formats, so they're in cogs, in buckets, without the necessity of having a server in between that can be expensive and might not scale so well in order to deliver the imagery. Everything is unified in this catalog, and finally we have this view, this data explorer in Terea that we have different versions of for different communities. So we have raster data pipelines, table data pipelines, vector data pipelines, and then this metadata editor for data styling and publishing. So this is done through the catalog, this is done through the raster manager, the table manager, and the vector manager. So let me talk a little bit about the raster manager in particular. So its purpose is to ingest many different tiles or data come from different places. It can process many hundreds of thousands of tiles, in short amounts of time, scaling to many, many different compute resources, and then shrinking back to zero when they're not needed. It also has follow-on actions so that it can calculate derived data. So if you're looking at daily, maybe you want to calculate a monthly aggregate or an annual, or maybe you have two variables that are required to generate a third variable. It comes with a web API application that we'll see now for preparing that data, and a set of APIs to consume the data, and all of the data is published in cloud-optimized geodesks. So essentially, the process is that when you configure your data in the GIS manager, it creates two cloud storage buckets, one for upload and one for data. Oops. So, and then we also have these different roles. So similar to the editor roles within the catalog, we have roles for data managers, and these are not the same. So the people publishing the data on a platform and documenting it are not always the same as the people that are generating data and uploading it. So the flow is like this. We define the shape of the data that we want to upload, so the time, the dimensions, the extent, the resolution, the format of the raster coming in. And then that goes to an upload bucket. An automated job wakes up, a cloud native function in this case, and then the data is processed. And finally, if it passes all the tests, the database is updated, and the final public data, well, not necessarily public, but the endpoint where the data is consumed is made available in another bucket in POG format. So inside we can have a single layer, or we can have what we call a map set. So a map set is essentially many layers with the same unit, but for either a different time period or a different dimension. So it could be gender or species or something like that. We can also, oops, these slides got a bit mixed up. Yeah, this one should come next. We also have grids. And this allows you to have many tiles that can be disjoint or even overlapping. So sometimes you have streams of data, maybe UTM tiles coming in, and you need to create a composite file. And this is one way that you can do that. And then a mosaic data set is basically combining those two things together. So you can have holes, or you can have overlapping, and it also has dimensions. So we can style the data directly here, saying the different cutoff points, which colors should be used, using different approaches. And then we can also specify the dimensions, so the list of crops, the what dimension, or how time is managed. Is it every 5 days? Is it a 10 daily, decadal data? This is just a screenshot of how it looks, the web application. And this is some of the final outputs. You'll see this is a cloud storage bucket. There's one for these different data sets. In this case, it's a level 2 actual evapotranspiration, I think that is. And it comes along with a JSON file in the same bucket, which means that if you don't want to deal with the APIs and you have some Python, you can very quickly pick up the key information about the file. So the JSON file and the GeoTIFF file have the same name, just a different extension. We have something similar for the table manager. So here the table data sets are managed like the rasters in many ways. First of all, a contract is set up. So this is a data set provided by an external company called Marcura, and they track the ocean vessels and their cargoes and where they're going. And so there's a contract that's defined, again, showing the same units of measure and the data and the formats. And I think I don't have the slide for this one. And so here we have two buckets, same approach, an upload bucket and a final processed bucket. And so every time there's an update where these boats, these marine vessels are moving, that is dropped into the one bucket. It's checked, validated, consolidated, and pushed into, in this case, the data warehouse. So one useful feature that we do have is being able to extract what we call zonal statistics from raster data. So this is coming back to the analysis functions that we saw previously. At the moment, it's a form request with some manual people behind it, but we're trying to automate this so that you can request for a data set to be kept up to date in terms of the data warehouse representation of a raster data. So let me talk a little bit about the I'm almost at time technology very quickly. I'll skip this one, which is more standard. These are some of the key products that we're using. Everything is running on the Google Cloud platform. That's allowed us to move very quickly, but it does mean we have some strong dependencies on Google specifically and can't readily move to some of the other platforms. CCAN is used on the metadata, Terrae.js for the front end. GeoServer we're still using, but increasingly less and less. Stack is coming soon. Neo4j is a new component just being edited that will allow us to have a graph database across the whole of the platform. Elasticsearch is speeding up the access to data. We're using Google Earth Engine for some of the back-end analysis or to publish data that's available there. We also are using Apache Airflow and Spark for the data engineering pipelines that allow us to ensure the data is flowing and up to date. It comes with some nice consoles and things like that. Okay, so the key takeaways, we have a thriving community around it. You see the statistics yourself on the screen. These are a little out of date, but you can see, for example, an 80% plus year-on-year growth. We served 21.5 billion requests. And I think looking at the analytics, I think it was every country in the world is now accessing the platform. So actually, it's only 214, it says here. So it wasn't every country. So the other key takeaways is the platform is used to analyze and compare data sets on food and agriculture and draw insights. We include a comprehensive data catalog with extensive data from diverse sectors and sources that you yourselves can contribute to. It can be configured for different communities, thematic or regional, and the system comes with guides, resources, and video tutorials. We also offer training sessions for specific communities throughout the year. And that is the end of my presentation today. So thank you very much for your attention.
Well, thank you very much for this very informative presentation, Carl. So the platform is really fantastic from all aspects, I would say. So it's not only provides data access to a large amount of data sets, but it is very rich also in terms of analysis capabilities. And it's really nice to see all these use cases as well at the regional, national, and even international level. So thank you very much. So we have about 15 minutes for your questions and also maybe a discussion on different aspects of Carl's presentation. And actually, Valentine already asked a question in the chat. So if you want, you can ask it also directly, Valentine, or otherwise I can read it.
No, that's fine.
Yeah.
Hi, Carl. Valentine speaking. I was asked by Anton to join this session, and thank you very much for making the effort of showing the progress and the uptake. Yeah, I was wondering, in the beginning you mentioned an hexagon as maybe just an illustrative method or technique of harmonizing and allowing multi-source data to be intersected, but maybe it's actually operationally used. I don't know exactly how that comment landed in the end, and whether or not it landed in the platform. Yeah.
So today we do not support hexagon, or more specifically H3 from Uber formats. We have been treating them as individual shapefiles and processing them as vector plus tabular data. What we're actively working on is to make them well-known areas in the platform, so that they have a clear separation between the data warehouse. So if you're using the H3 code, you would be able to then access data. And that means that you will also be able to get the auto-magically generated statistics for those hexagons. So we're increasingly seeing data being published in that format. And I think it's a growth area, but we're not there yet. It's something we're working on, and we hope to support better next year.
All right, thank you. Cheers.
Okay. Thank you. Nanette?
Yes, okay. Thank you very much for your presentation. One of the first slides you said about the data, who is authorized? I like to know who is authorized to use it, because it's fantastic data source, of course.
So there's no simple answer to that. So the data is FAO data in general is Creative Commons 4. So we try to make the data available for people to use. So that will be the default license for data generated by ourselves. Unfortunately, not all data can be made available in that format. So an example is some of the sensitive animal health data, or data that identifies a specific location of a teak tree or a pesticide store.
Yeah.
So there are many examples where the data is not public. And the way that the sharing mechanism works is that there's an organization. So it could be, let's say, the animal health group of FAO, and they decide who is in that group. And they decide which data that's owned by that group is public and only visible to members of the group.
Yeah.
So that's at a very sort of high level, more or less how it works. So it's federated. So let's say somebody in the University of Twente had an organization, they published some data. They would have then the owner of the organization. So there's this concept of an organizational owner. Somebody from the University of Twente would decide this data is public, this data is private. Only people I want to see it can access it, as opposed to anyone can use it for any purpose. I hope that went some way to answering your question.
That you can request if you can be a member or authorized for certain data layers.
At the moment, you don't even see it exists. So you won't even see the data. So there's also a difference between downloading data and viewing the data. If data is completely confidential, then you will not even see it. So if you log into the data if you use the data catalog, or I log into the data catalog, we will see slightly different results. We will see different things. If I look at the epidemiology site for Kenya, I would see different results to somebody that's an epidemiologist in Kenya, because they have some data reserved for themselves.
I will have a look. Thank you very much.
Okay, thank you for the question as well. So are there any other questions from participants? I hear a few questions actually, so maybe I can start, and meanwhile maybe others may also continue to ask some other questions. So Carl, you mentioned that it's possible to upload the data to the platform, so it's possible for people to at least ask for it. And I wonder if you have certain criteria that needs to be met with these data sets, because it might be possible that somebody did a kind of case study in a region area, which might be, of course, a valuable data set, but maybe from spatial extent point of view, it could be something small for you, or you may say, okay, we are interested at least a country level data. Do you have such criteria in place, or what's the procedure to make the data published on the platform?
So firstly, there are two concepts of published. One of them is that it appears in the catalog so that people can go and find it. And the other one that it appears in an application. And so they're slightly different. You might have a data set that's in a catalog, but it's not in an application. Secondly, the data on the platform requires an FAO sponsor. So we don't typically charge people to upload data to the platform unless we need to do data engineering work. But there's a FAO sponsor involved, and their purpose is really to provide the trust and the accountability for the data that's eventually published. Let's say you have I don't know, indigenous people data sets in some small region of Brazil. So that data set is still very valuable, but it would first need an FAO sponsor to check with the head of profession within FAO that this is a trusted source of data. And then you would also need to provide the metadata record that specifies where it came from, the copyright, the limitations of the data. So you can upload any data. It could be, for a very, very small area, very, very specific, or it could be a global data set. Then to get the data into a particular application, now it becomes the owner of the application, which again is managed through the data catalog. So let's say you have the indigenous peoples database and you want it added to the global water database, the global water site. They might say, this is just not relevant. We do not want your data, or the quality is not right, or it conflicts with another available we have. So we do have, confusingly, often similar variables from different sources. That's because it fits together with a particular data set. Agricultural stress might be using one kind of precipitation, whereas water productivity might be using a different source of precipitation. So it's not that you can't have two different variables on a platform, but then the owner of the application is making the choice of which one is the most appropriate to be included in their application. I hope that answered the question.
Mm-hmm. Thank you. Yes. So eventually, a connection with FAO, a group, is required to make the data at least available. And applications are also linked to FAO sponsors, I believe, right? So there should be a unit that is willing to have the application.
Yes. So, I mean, we don't just let anyone log in and upload any kind of data. There is sort of accountability and a responsibility, which means that if you're publishing, I don't know, crop type maps, then it has to be done at least with some oversight with the crop type map people in FAO, just to make sure that we're not putting sensitive, conflictual, poor data up there. As long as the data is coming with a quality information on the mechanisms that we use for generating it, and it's not controversial in some way, I think most data would be, and it's related to food and agriculture, would be accessible to the platform.
Okay, thank you. Aditya posed a question in chat. So Aditya, if you want, you can also ask it directly. Otherwise, I can read it.
I think they're saying they don't have a mic. I can read it, or maybe you want to read it. So they're asking if Google Earth Engine. So we were using a lot of Google Earth Engine. More recently, we don't do much processing on Google Earth Engine for several reasons. So now we are using a set of back-end Python services that are cloud-native services, so they wake up, process the data, and disappear to minimize the costs. The places where we still use Google Earth Engine is when there are complex models that have been written using Google Earth Engine. So it's not simple raster arithmetic or summaries. But equally, we're using some of the backends, like some Fortran systems or R systems that do analysis. So we're using quite complex computes. So rather than virtual machines, we're actually using a combination of cloud functions and I've forgotten the name. Another kind of, it's a virtualization anyway, that allows us to quickly scale up. So that means we can drop to 0 instances of the analysis service to hundreds, depending on demand. And we've tried to do that throughout the platform. It's a double-edged sword because on the one side, we're able to move very quickly, but on the other hand, we're dependent on a specific cloud provider for that.
Okay. Previously, FAO data systems were in a local data center, or what was the situation before you established the platform? Can you provide some information about it?
Yeah, so I think there are 2 reasons, 3 reasons maybe, that we've progressed along this. One is we had a decision to decommission our data center in premises. There are many different applications that needed to be decommissioned, so we're already moving to the cloud. That was one of our first drivers. The second one was fragmentation. What you'd find is that the same group were downloading, publishing, manipulating data because they both wanted precipitation data, and it happened to be the same precipitation data, and it was documented twice. So one of the second big drivers was if we could create a platform that could be reused to serve these different communities, hopefully we would reduce the amount of effort in duplicated analysis of data in one place, and also development of the front-end dissemination systems. And there was a third point, escapes me. I can't remember what that point was.
Okay. How long did it take for you to do this transition? So because it's very clear it's a significant work, but can you provide some insights about the timeline approximately?
Okay, so it was needed. That was the third point. In fact, there was a flagship project hand in hand that needed this platform in order to be able to deliver analytical services. So in terms of the timeline, it's work in process. We like to joke that we are building the airplane as we're flying it. So we're not finished yet. Still a long way to go. But it took us about, I think, 6 months to get the first version up. And 2021 is when we started this stuff. And we're constantly iterating. So weekly, there's updates of data, functionalities, and we're constantly working behind the scenes to make it better every day. Yeah, I guess I should have a big shout out in particular to the open source community, because without them, we never would have been able to do what we've done. We're very reliant on open source tools that have made this happen.
Wonderful. I was expecting to hear like 3-5 years. So six months is really amazingly short period from my point of view. Really, congratulations. But of course, it's not only 6 months, so there's a lot of experience, and I think the components were already in use. So basically, you moved them from your data center to cloud, but integrating the things and eventually moving everything to cloud is not a trivial task. I think you really did a great job there. Congratulations. Actually, we know a little bit behind the curtains as well, because we have been working with Carl's group throughout the year. And in fact, if anybody from ITC would be interested to know a little bit better how to make their data available in the platform, or develop custom applications, we have also some experience now at the ITC side, and we can be maybe the bridge, and we can also facilitate somehow the collaboration between ITC and FAO. Okay, so are there any questions from the participants? Okay, if not, I want to thank again Carl for this great presentation and insights about the platform that you have been developing for a while and operating very successfully. I hope we will have some, in fact, we will have an application coming quite soon at the end of the year. It's called City Region Explorer. So it will be working on the platform. We have the data that is already there, and we developed, in fact, some custom analysis functionality that is available already on top of the platform. And our experience was also really, really great. So seeing all the infrastructure that is in place was really quite nice.